Now let's look at some of the basics that make a linked list work. Essentially, the linked list is a container class, meaning that its primary purpose is just to store data and have the user of that class be able to access that data at some point. Each node that we have is going to be dynamically allocated and contain a single piece of data, whatever we're storing, whether that be ints, users, movies, etc., accounts. So if we have 100 items stored in our list, then we're going to have called new 100 times, which means that eventually we're going to have to call delete 100 times as well so that we can clean that up. So unlike the vector or array, where we might have one large allocation of 100 items, instead the list contains many small allocations, which again makes it easier to remove things or insert things into that list. The class is going to need to contain, at a minimum, a single pointer that typically points to what we would call the head of the list. So this is going to be not necessarily the first item that's put into the list, but the item that is at the front of the list. This is going to be the only node that we're going to have constant access to. So we're not going to know right offhand what the memory address of every single node in the list is. So we're not going to be able to randomly go through the list and access nodes in a random order like we could with an array. So we would need to iterate through the list to get to other data, which is how we commonly use lists. So typically, if we have a linked list that we're needing to process through that list, we would just go through the entire list and do whatever we need to do with that data, print it out, render it, check to see if it is of a certain value, etc. We can also have a tail pointer as well, depending on what we need to do. So this isn't necessary, but it could be advantageous for us. For example, if we need to add to the end of the list. So if we wanted to do something like queue ordering, where we have a adding to the front, or I apologize, adding to the back and removing from the front, then we would want to have a tail pointer so that we could add to the back at an order 1 complexity. Here we have a couple examples of some common node structures. Just for simplicity here, I've made these with integers, but in reality, they would probably be templated, just like any other data structure, so that we would have a lot more flexibility in what we store. The one on the left here, we can see, is for a singly linked list. And basically what that means is that each node is connected to one other node, that node being the next one in the list. And we have a little diagram here of a singly linked node. So the node is both the box and the arrow. So the box is representing the data. In this case, we're storing a 5. And then the pointer is that pointer to another node. In this case, we're pointing to a null pointer, which is going to let us know that there is no node after this one. So this would be the last one in the list. Over on the right-hand side, we have a doubly linked list node, and we can see that there's just one small difference between them, and that is that this one contains 2 node pointers. So we not only have a pointer to the next node in the list, we have a pointer to the previous node in the list. This will make it easier to do some things at the cost of some additional memory overhead, right? So in this example here, each node is 8 bytes for a singly linked list because we're storing an int, which is 4 bytes, and then a node pointer, which is, I guess, depending on the type of application we're running, this could be 4 bytes or 8 bytes. If we're in a 32-bit application, this would be a 4-byte pointer. If we're more in the common 64-bit application, then this would be an 8-byte pointer. So this node here, let's assume that we're dealing with 64-bit applications. So this would be a 12-byte node. So that would mean that every single piece of data that we're storing within our linked list is using 12 bytes to store that, right? So we have the integer, which is what we're actually wanting to store, right? That's the pertinent information. And then we have to contain also this pointer to the next piece of data in the list. So that means that an array of 100 ints is just 400 bytes, right? 4 times 100, whereas a linked list to contain that same information would be 1200 bytes because we have to store those additional pointers. Over on the doubly linked list side, obviously we're adding an additional pointer, so that's going to add an additional, let's say, 8 bytes for a 64-bit application. So therefore each node in a doubly linked list would be 4 bytes for our int, 8 bytes for our next pointer, so that brings us up to 12, then 8 bytes for our previous pointer, bringing us up to 20 bytes per piece of data that we want to store. Now, why would I use a doubly linked list over a singly linked list if we have this additional memory overhead? Well, a doubly linked list is going to make it much easier to insert and remove things because we know who the previous node is, and it's going to make it easier to tie the nodes together when we either insert or remove. And we'll see that once we get to the diagramming here closer to the end of the lecture when we start going over the lab documentation. So we've mentioned nodes a couple of times now, but we haven't really gotten into the details of what a node is. Nodes are very common for many data structures, such as the list and the tree that we're going to get to during week 3. And these are going to be used primarily for any data structure that is non-contiguous. And we'll look at a couple of examples here in the next slide.